Hello, welcome to Econometrics Melody. In this video, we will discuss about the process of estimating the variance of OLS beta. We know that n-1, the ratio of the variance of a sample and the variance of population, this has a chi-square distribution with n-1 degrees of freedom. So while calculating the sample variance, we divide this term by n-1 so that the expected value of the sample variance should be equal to the population variance, and this gives us an unbiased estimator of the population variance. Similarly, the variance of the population residual, this is given by sigma square in our classical linear regression model, and this is the linear regression model for the population, and this is the linear regression model for the sample. If the variance of the residual for the population model is unknown, we need to estimate making use of the variance of the sample residual. And if variance of sample residual is s square, then in order to calculate the unbiased estimator of the variance of the population residual, we need to calculate the variance of the sample residual and what should be its value. Basically, what is the dividing factor? Like here we have n-1, so what is the dividing factor in case of the variance of the sample residual, so that we get an unbiased estimator of the variance of the population residual. So this is what we are going to find out today. And this is necessary because the conditional variance of OLS is beta estimate. This is given by the variance of the residual in population model into x transpose x inverse. Now we need to estimate this by the help of the sample residual. And these are some of the properties that are going to be useful. So the trace of AB's matrix ABC, this is equal to the trace of CAB and trace of PCA. We follow a cyclic permutation ABC, BCA, CAB, and so on. So this is true for any of the matrix. And expectation of trace of AB, so this should be equal to trace of expectation of AB. So we can interchange the order of performance of this expectation and trace. And also we know that in a classical linear regression model, y is equal to x, b plus e, me, this is equal to the error term itself, my, this is also equal to the error term itself, and mx, this is equal to 0, where m is our residual maker matrix. So y, this is equal to x beta plus e, this is the linear regression model for the population, and y is equal to x beta plus e for the sample. And the sum of the square of the residual for population, we can estimate making use of the sum of the square of the residual from sample. So let us write E transpose E, the sum of the square of the residual of sample, and let us write the population counterpart. So H we know m e, this should be equal to the residual term, and my should also be equal to the residual term. We know this relationship either for the population or for the sample. So let us substitute it by the value of the population. And is the residual maker matrix. This is idempotent matrix. We have this relationship. So this is simply equal to E transpose ME. And we know that E transpose E, this is a scalar. So ultimately we are left with a scalar 1 into 1. So this is equal to the trace of this matrix. Actually, this is also of order 1 into 1. And if we apply the cyclic permutation property of the trace, then this should be equal to E transpose. Now let us take the expectation, conditional expectation on both the sides. And is the order of performance for the expectation and trace, they can be interchanged. So this can be written as the trace of expectation of this value ME transpose and then condition on x. Now we know that this residual maker matrix, it is the function of x, because m is the function of x. Therefore this can be brought outside of the expectation. It acts like a constant. So this is again equal to trace of, so let us assume the condition of homoscedasticity. Let us substitute that value, sigma square I. Is sigma square, it is constant. So we are left with sigma square and then trace of m. And let us substitute the value of m. This is further equal to, this is equal to sigma square. So m is of order n into n. because this x is of order n into k, and at last we have x transpose, that is k into n. So ultimately we are left with n into n, and in between we maintain this chain. This identity matrix is of order n. So the value of trace of this identity matrix, it is n only, minus. Now let us perform the cyclic permutation for this trace. Once again, the order of this identity matrix is of order n into n, as well as this entire matrix, this is also of order n into n. So the trace of this identity matrix is n, and now due to the cyclic permutation, the order of this matrix has changed. This is of order k into k, because x is of order n into k, x transpose is of order k into n, and in between they have maintained this chain. So x transpose, it has of order k into n, and at the last we have x, this is of order n into k. So ultimately this matrix is of order k into k. So this is further equal to sigma s square, and we have n minus x transpose x inverse and x transpose x, they are inverse to each other. That is why the product is the identity matrix of order k. This is equal to sigma square n minus, and the trace of kth order identity matrix, this is equal to k. Therefore S square must be equal to E transpose E, that is the sum of the square of the residual in the sample model. We need to divide it by n minus k, so that the expected value of x square, this should be equal to, and this is equal to n minus k, and then expectation of E transpose E conditional x, this is equal to n minus k into, and we have calculated the value of this as sigma square n minus k, and n minus k and n minus k, they cancel out, so we are left with sigma square. Therefore expectation of x square conditional x is equal to sigma square, and this is the unbiased estimator. Now as we know the, and if we don't know sigma square, this is what we wanted to find. So here we have, so we have estimated the variance of a residual of the population model, making use of the variance of the residual in a sample model, and therefore we can calculate the variance of OLS beta. So this is it for this tutorial. Thank you very much for your time. Thank you very much, Econometrics Melody.